In this video, we're going to look at depth first search, or DFS for short, as a graph traversal. So this is a way in which we can visit every single vertex and every edge of our graph exactly once. And we'll be able to do so in total linear time, meaning this will be big O of n plus m, where n is how many vertices we have, and m is how many edges we have. Now, we can use this in order to solve a variety of problems as well. This can be expanded on. So for example, we can use this to figure out if our graph is connected. Remember, connected means that we have in our graph between every pair of vertices a path connecting them. So this is important to know if, let's say, we want to send a message from one point to another point. This is only possible if there's a path connecting those points. So we'll be able to figure out if our graph is connected, and if it's not connected, we can at least find all of the different connected components of our graph. And we'll be able to compute a spanning forest of our graph. So these are things that we'll immediately obtain by doing a depth first search on our graph. Now we can also use DFS and expand it just slightly in order to solve a variety of other problems. For example, finding a path between two vertices, or finding if there's a cycle in our graph. So let's get to what the depth first search algorithm is. So this works on uses a mechanism of setting labels on vertices and edges. So the idea here is we're going to take, here is our, let's say, our vertex set and our edge set. And every vertex we're initially going to mark as unexplored. So this is a vertex we haven't yet visited. And same as edges. We'll initially mark all edges as unexplored. Once we get to them, we'll mark vertices as having been visited. So we've encountered that vertex. Remember, we're only going to visit a vertex exactly once. And for edges, we're going to mark them as visited in a different way. We're going to label them one of two possible things. Either we'll mark an edge as being a discovery edge. So a discovery edge would be an edge that we're using in order to discover a new vertex that we had not yet visited. Or we'll mark an edge as what we'll call a back edge. So a back edge, this is an edge that we have just now visited, but this edge is leading back to a vertex that we've already visited. So our first step is to mark all vertices as unexplored and all edges as unexplored. And then one by one, we'll go through each vertex in our graph, and if we haven't yet explored that vertex, if we haven't gotten to it yet, then we're going to call DFS on that vertex that's unexplored. So we're going to end up calling DFS once for each unexplored vertex. When we call DFS, we mark that vertex as having been visited, and then we will, for each instant edge, so for every edge coming out of this vertex, we're going to, if we haven't yet explored that edge, we're going to do so now. So in order to explore an edge, we need to determine should we mark it as a discovery edge or a back edge. Well, this is dependent on the vertex that this edge leads to. So we're here at a vertex V. Let's put it here. So here's our vertex V, and it has a few incident edges. It's going to some other vertex, let's say W, maybe other vertices as well. We're going to, for each edge, going to some other vertex W, so W is the opposite vertex along this edge. Use this vertex to determine whether this edge should be marked as a back edge or a discovery edge. If we haven't yet visited W, then we're going to mark E as a discovery edge because we can use this edge to discover this new vertex W. So if we haven't yet marked W as having been visited, meaning it's still unexplored, then we can set this edge as a discovery edge. It leads to this new vertex W, and then before we do anything else, before we get to processing these other edges, we're going to, in that case, call DFS starting from W. So then we would mark this W as having been visited. We would check its incident edges and determine if we should mark them as back edges or discovery edges. If we encounter a discovery edge, we'll follow that edge. And we'll kind of continuously make these recursive calls going from one vertex to the next along some discovery edge. Now, if this edge had led back to a vertex that we had already visited, meaning W had been marked as visited, it wasn't unexplored, then we'll label this as a back edge, indicating this is leading back to an already visited vertex. So we only get to processing these other edges of V after we've finished all recursive calls that we ended up making on W. If W led to some other vertices, we would follow that kind of chain as long as we could until we had nowhere else to go, and then we would come back and process the other incident edges of V according to our for loop. Okay, so let's see this in action. Let's say this is our graph. So you can immediately tell just visually that this isn't a connected graph. We have two connected components here and here. And let's say that we start our depth first search call on vertex A. So in this graph, I'm going to mark, let's just assume everything is marked as unexplored. This will just be if it's unmarked. And I'll use a kind of red circle here to mark a vertex as having been visited. And for edges, we'll mark them this way if they are discovery edges. And for back edges, we'll mark them this way to show that they lead back to a vertex that's already been encountered. Now notice when I'm marking these edges, I'm going to give an indication, even though our graph is undirected, meaning every edge is undirected, when I label them, I'm going to give them a direction just so that later we can tell how we got to a vertex. Okay, so let's say we start at A. So we call DFS on A, which means we mark A as having been visited, and then we're going to consider each incident edge. So we've got a few to choose from, one that goes to B, C, D, or E. We could choose any one of them, but in order to be consistent, let's just say that when we've got a choice of many edges to choose from, just so that we can deterministically do this, let's just say we choose the vertex to go to which comes earlier in the alphabet. So between all of these, we could pick any one of them. Let's just say we pick B to go to because it leads to a vertex that comes earlier in the alphabet. So we're going to mark this edge as a discovery edge because we haven't yet visited B. So I followed this edge from A to B. Now we call DFS on B. So we mark B as having been visited, and we'll consider all of its edges which haven't been marked. So we've only got one, which leads to C. C hasn't been visited, so we mark this as a discovery edge. Now we call DFS on C, which means we visit C, and C has a few edges to consider. So we've got going to A, D, E, or I. So again, let's choose the one that goes to a vertex earlier in the alphabet, which is A. But A we've already visited, so this is our first back edge that we encounter. So this is a back edge going back to vertex A. So now we'll look at the other edges. So from D, E, and I. So let's go to D first. So we've got a discovery edge because we haven't yet visited D. We're going to visit D now and we call DFS on it. And then we'll look at all incident edges to D that haven't been marked. So we've only got one, and that goes back to A. So we're going to mark this as a back edge. And we've finished all incident edges that we could consider on D. So we're going to work our way back the recursion stack. How did we get to D? So this is important now why we labeled those edges with a direction. How we got here was we went through C. We called DFS on C and we were evaluating an incident edge. So now we can look at the other incident edges of C. So we're going to follow this one next. We mark this as a discovery edge because we haven't yet visited E. We're going to do so now. So we mark E as having been visited. And we'll mark this as a back edge because it leads back to vertex A, which we've already encountered. Oops. So now we've evaluated all incident edges on E. How we got here was through C. So do we have any other incident edges left of C to consider? We do. We've got one which leads to I, and we haven't visited I yet, so we're going to mark this as a discovery edge, and we'll visit I now. I has no other edges incident to it, so we're going to work our way back until we find somewhere else, some other route where we could have taken. So from here, we got here from C. C has no incident edges that we haven't marked, and how we got to C was from B. B has no other incident edges, but how we got here was from A. A has no other incident edges which haven't been marked, so we're finished because we had initially started our call from A. So now we're not yet finished because remember our DFS call, we had two, kind of in the last slide here, we had two algorithms, one on the left and one on the right. This was our initial DFS call, and we called DFS on a specific vertex for every vertex that hadn't yet been marked as visited. So our first DFS call here, this was for each vertex, we called DFS, and then we had some algorithm DFS here, how we accomplish this on a particular vertex. So we had initially called DFS on A. This was our starting point. And then once we called DFS on A, we ended up calling it on B, and then C, and then D, and then E, and then I, just through our recursive calls over here. And then we finished all of those recursive calls. We finished our original DFS call on vertex A. So now that we're back here, we're going to check for each vertex. We already started with A. For each vertex, has it been marked yet? So we're going to check now for vertex B. That has been marked, so we're okay. So let's just say we're going in alphabetical order here. For vertex C, that's been marked, so we don't call DFS again on it. D, E, those have been marked. Now we get to vertex F. So the second time we called DFS from our left algorithm, I'll go back in a moment. The second time that we called DFS from vertex F, because F hasn't been marked yet. We already marked everything that we could reach from vertex A, which was our starting point. Now we still have other vertices in our graph that need to be visited, so we're going to call DFS on that. So DFS on F, we mark F as having been visited, and we'll consider it's got two incident edges, which one we should traverse first. Let's say we go in alphabetical order again, so we're going to mark this as a discovery edge because it leads to new vertex G that we haven't encountered, and we mark G as having been visited. We'll mark this as a discovery edge because we haven't encountered H yet, and we'll now visit H. Now this leads back to a vertex we've already encountered, so we mark that as a back edge. H has no other incident edges unmarked. Now we'll go back to G. This is how we had gotten to H in the first place. G has no other incident edges which haven't been marked, so we go back to F. F has no others, so we're finished with that DFS call starting with F. So now we have to see, was there anything left in our graph that we haven't yet visited? We already marked F as having been visited. G is okay, it's visited. H is okay, it's visited. I is okay, it's visited. So we're done with all of our calls to DFS in our graph. We're done with our entire traversal. So we've marked every vertex as visited, and every edge has been visited, and we've labeled them as either discovery edges or back edges. You'll see a few of the important properties that DFS has and other applications of it in the next video.